in the standard Haskell notation, a tree is a data type with those two constructors, ND for node and LF for the leaf. And sorry, we're not. I'm just using Haskell as a nice notation, but I'm not buying into lazy evaluation here. That has got nothing to do with it. And the type parameter A here, the tree type has a parameter A. That's the type of values. And we are completely separating the building of the game tree and the evaluation of the game tree. That's just for simplification. Normally, of course, the two things are interwoven, but to focus on the evaluation, it's easier to assume that the tree is already there. Now, of course, you will typically not be able to build the complete game tree because it's much too large. And so the terminal positions will not necessarily really be final positions in the game, but they might be cutoff points where you've decided, the game tree generator has decided, I don't want to go any further because it's just getting too deep. And then you assign some heuristic value to that node, which means, or rather that leaf, which means, of course, the heuristic values are not necessarily just infinity, plus or minus infinity and zero, but could be anything in between, which comes from the heuristic evaluations. And so initially, in the first half of the talk, we assume that the values are linearly ordered with top and bottom elements. And so I'm not using plus and minus infinity because that suggests numbers, but it's really, we're really not dealing necessarily with numbers, but any linear order. Yep. But you can always think numbers, that's accurate enough. So we have this minimizer and maximizer, and the specification of what we want to achieve is the evaluation of the game tree. And we have two evaluators. Max min is the maximizer that takes the maximum of all the minima of the children. So of course, the value of a leaf is always that leaf itself. But the value of a node, there you have to map the opponent, the min-max function, over all the children, TS, and then you take the maximum of that. And dually, here's an example of a game tree. At the lowest level, we have leaves with values, and then above we have alternatingly the maximizer and the minimizer. And so if we evaluate the tree from the bottom up, of course, we take the maximum of the leaves, which, for example, here, the 9 is the maximum of the 5 and the 9. And then again, we take the minimum of all the values, so the 3 and the 9 here, whatever. The 3 is, of course, the minimum of 3 and 9, and 1 is the minimum of 1 and 7, and then the maximizer again takes the 3. And so that's just the mathematical definition of what the value of a game tree is. And I'm showing you everything just from the point of view of the maximizer, because everything from the minimizer's point of view is just dual, and it's a waste of space to show you both. So this is the starting point. This is what we want to compute, the game tree value, but we want to compute it with as few, and we want to prune as much of the game tree that we can. So we want to evaluate as little of it as possible and still get the precise value. The max-min function is executable, but it's traversed the whole tree. That's not ideal. And alpha-beta pruning is the standard solution to minimizing what you have to look at. And essentially, the idea is you compute the value of the tree, but you avoid pointless subtrees. How can there be pointless subtrees? Well, here is the basic idea. In an extreme situation, you are the maximizer, and you found a move that forces a win. Well, then no other move ever needs to be considered. So once you've won, that's it. You can discard the rest of the game tree. in general, we generalize this, and we have two search parameters. So just instead of just looking for wins, and we have an interval A and B, and we're looking for subtrees that lie in that interval. And so what is the A and the B? The A is the value that the maximizer is already guaranteed from previous explorations of the tree, or not previous explorations, from explorations of other parts of the tree. And that means the maximizer is not interested in any value less than A, because it already knows I can get A somewhere else. Similarly, for the minimizer already knows it can achieve a value less than or equal B, so it's never going to look at anything beyond B. And so that's why this interval is all we are interested in. And so, yeah, that's only elements in that interval are of interest. And that allows us to cut down the search. And the maximizer tries to increase that A bound, and the minimizer tries to decrease the B bound, until eventually, in fact, the A and the B overlap, or B goes below A, and then we don't need to search any further. And so here is an example of how this proceeds. So this is, again, the same game tree that we saw earlier, but now we are trying to search the game tree with the alpha-beta strategy. And we start out here, and that means we start out with the parameter A being the bottom value and B being the top value. And then we proceed through the tree, and over time, this will change. We will get better bounds than just top and bottom. So we go down here, we still have only those values. We go down here, we still have only the full bracket, and then we're the maximizer. So we first go down into the 2. The 2 is certainly in the interval, so that's great. So the value so far is 2. And then we go down there, then the value is 3. And now we come back up, and now we know that the maximizer is not interested in anything below 3. So we can increase the lower bound. Sorry, the upper bound. So the 3 is now the upper bound. Why? Because we will see in a moment. So we now go down. So this is the minimizer, and the minimizer knows that if it allows the maximizer to get into the first subtree, then it can get a value of 3. And so now the minimizer goes down here, and what does it find? It finds it's looking at that interval, and now it goes into the first subtree, and it finds a 5 there. And then it says, oh, the 5 is outside that interval. Why? Because it's bigger than the 3. And why shouldn't I be looking at anything anymore? Because I know now that the value of this subtree is at least 5. The maximizer might even be able to achieve more, but the 5 is already worse from a minimizer's point of view than the 3 that the maximizer can achieve over here. So it's completely pointless to keep on looking at that subtree, and you again you go up and then you go up further. So this is the point where we've actually managed to cut off part of the tree, because it's always this interplay with dual minimizer and maximizer, and the maximizer trying to achieve something large and the minimizer something small, but the minimizer wants to avoid allowing the maximizer to achieve better values. So that's the main idea. I'm not going to go through the rest of the example. So now we have a function called AB max, and that's the alpha beta version of the maximizer. And it takes these two interval, it takes the interval bounds, and it takes the tree that it's supposed to evaluate. And that function is based recursively on a function that takes again the interval, but it's has an S here at the end, so it takes a list of trees. And so it's going through the list of children of the node. And now what happens is it'll first look at the tree T, and it'll evaluate this, but now from the opponent's point of view, from the minimizer's point of view, and then it'll take the maximum of the current lower bound A and the new value. And so A prime is sort of our new value of A. And then it tests, has the new value of A already gone over our upper bound B? Well, then we're basically finished and we can return that value. And otherwise, we keep on recursively calling the evaluation of the children, but now with an increased value of well, possibly increased, because here this maximum, of course, is not necessarily bigger than A, but it might be bigger than A, a possibly increased value of the lower bound and the unchanged upper bound. So that's all there is in terms of code. So it shouldn't be too hard to analyze. And so the question is, what is the correctness? And this is what we want. We want that if we call the alpha beta function with the full interval, then it should really compute the true value of the game tree. Now, of course, you can't just replace the top and bottom by arbitrary values. It will not, in general, give you the true value of the game tree. And so you have to generalize this statement somehow. You have to generalize it to, well, yeah, beyond this naive generalization where you've replaced the two constants by arbitrary values. And this is the generalization due to Knuth and Moore already in 1975. So the alpha beta pruning goes back to the 50s or late 50s. And then in 75 is the first really sound mathematical analysis. And in the rest of the talk, you can assume if you see in AB, that's the value of alpha beta pruning. So here it's, in our case, this AB max function with the parameters AB applied to the value T, and V is the real value of the tree. So it's the maximizers. We'll always look at the maximum point of view value. And then they prove the following property, the following generalized relationship between the alpha beta value and the real value. And the correspondence is the following: if the alpha beta value is below the lower bound, then the real value is also below the lower bound. If the alpha beta value is in between lower and upper bound, then it's actually the correct real value. And if the alpha beta value is above the upper bound, then the real value is also above the upper bound. And they prove they prove this property of the algorithm, so it's now generalized to arbitrary A's and B's. And if you then plug in top and bottom, then, this is a notation that I'll be using for this complex relationship. I'll just use this funny relation symbol in the middle. And I will often ignore the bounds A and B. Question? No, okay. And then as a corollary from that theorem, you get that if you call the alpha beta algorithm with top and bottom, you do get the true value. But in the middle, you might get other values, and we'll see what the point of that is. So this is called fail hard. And why is it called fail hard? Because it says that if you get to the end, that's an equation that I haven't shown you, a defining equation I hadn't shown you yet. I'd only shown you defining equations for the evaluation of the children when there is at least one more child. But if there's no more child, then our version of alpha beta pruning, called the fail hard version, just returns the lower bound. And that is a little bit imprecise because you will then get this relationship in general that you will always return the lower bound as the alpha beta value, even if all the elements in your, if all the children have values less than the lower bound. So you could, if you keep track of their values properly, you could return something that is closer to the real value than just this brutal cutoff of A. So this fail hard is in some sense not optimal, but it does the job in the sense that if you start with the top and bottom elements as the full interval, then you do get the precise value. So you get imprecise bounds in general, but precise bounds for the complete interval. And now let me compare a second version. So we have looked at fail hard, and now we will also look at fail soft. So this is just for repetition, the code for fail hard. Fail soft now, that was introduced only in 83, does the following. Our function AB maxis that goes through the list of children. So the prime here indicates that we're in the fail soft version. It takes again an interval, but it also takes a third parameter, which keeps track of the real values in case they are below the A, and then the list of children. And so if there are no more children, then we return M, which in this case, if nothing has happened, then it would be bottom, but it could be something else. And so we have this additional parameter that we can return. And this is what happens in the case if you have more than one child. Sorry, if you have at least one child, then you again recursively call the opponent to evaluate the tree T, and then you take the maximum again, but not of the lower bound M, but the maximum of the current approximation of the real values of the children. And if that goes above B, then you return that, and you don't return the A, and otherwise you return you recurse for the rest of the children. So the key idea is really you have this additional argument that approximates the real value of the children better in case the children all have real values below the lower bound that you're interested in. And let me just contrast those two relations. This is the relation that Knuth worked with. And I've given this funny symbol. It's denoted by that funny symbol. And if you have some interval AB, and the definition was, just to recall it, if y is below a, well, then we know that x is also below a, but we don't know what the relationship to y is. And if the value of y is above b, then we know that x must also be above b, but we don't know exactly where. And if y is in the middle between a and b, then we know it's equal to x. And this is actually, as the symbol suggests, a symmetric relationship that doesn't look symmetric when I explain it like that, but it is in the end symmetric, provided A is less than B. That's something that will sometimes, I will implicitly assume, and it makes sense because once A is above B, then we have the empty interval, and then it's not of interest anymore. So what's the other relationship now that fail soft will satisfy? It's a stronger version of this one, and I will just call it bounds. So y bounds x. The term bounds isn't optimal. I hope you have some better ideas. And it's almost like the previous relationship, except that some relationships are not allowed, namely these that have just disappeared. And so now, if y is less than a, x must be even lower than y. It can't be above y. And similarly, if y is greater than b, then x must be even greater than y. So now the y really determines the x much better than in the previous relationship. Indeed, this new relationship implies the previous relationship, and the new relationship is not symmetric. I would love to get a better name for bounds then, because y bounds x is really it's a bit of yeah. In some sense, you want an asymmetric symbol here, but I don't know which symbol to pick because it's not clear whether y is less than x or y is greater than x because of the symmetry in the with respect to the lower and upper bounds. So I'm looking forward to any suggestions from the audience. So y is sometimes an upper bound and sometimes a lower bound for x, depending on which side of the interval you're in. So now Fishburne defines this relationship bounds, and then he says, well, let the value AB prime be the value of this fail-soft version of alpha beta with arbitrary parameters AB and this third parameter which starts at bottom. And let V again be the real value of that tree T. And then he says, he just states, he doesn't prove anything, then this fail-soft version of alpha beta bounds the real value in the sense that you've seen on the previous slide. And he also writes that fail hard and fail soft search the same part of the tree. He just writes those things. There's no indication of how to prove this. And of course, when verifying it, I did go through the details, and he's right on both counts, but he misses the point. Because he then claims, oh yeah, fail soft is better, but it's unclear why fail soft is better. You may think, oh, fail soft is better because fail soft satisfies this relationship, which is stronger than the other relationship that Knuth proved for fail hard. But now we'll see something surprising. So recall Knuth proved that the fail hard variant was in this relationship to the real value. Thanks to Fishburne, we now prove that fail soft version is in the stronger relationship bounds to the real value. But what Fishburne didn't notice that fail hard is already in the stronger relationship with bounds. So we now have that both fail hard and fail soft are in this relationship bounds with V. So this appears not to have been, I couldn't find this relationship in the literature. And so why is fail soft still better? Well, because, and that's the real thing that he doesn't state, fail hard bounds fail soft. So that tells us in a nutshell that fail soft provides better bounds than fail hard, while searching the same part of the tree, which is of course a bonus. But is it really a bonus? Because how does that help? After all, both of them, fail hard and fail soft, yield the real tree value if you call them with the full interval. So why are we worried about what happens if you're looking at parts of the interval only? Well, Fishburne, who came up with this idea, says, well, I'm not quite sure, but here are some ideas that could work. And the ideas are based on this fact, namely that games are typically not just trees, but they're graphs. You can reach the same position via different paths or transpositions of the same position, which are essentially, from an evaluation point of view, identical. And so this is vital for efficiency reasons to take this sharing into account so that you don't, like in a tree, you don't evaluate that same subtree again when you come to it from a different path. However, of course, alpha-beta pruning has also not just the tree that it evaluates or the subgraph, but also the bounds A and B. And it may be that if you get to a certain position from one path, you have certain values for AB, but if you get to that position from another path, then you have different AB values. So how can you share that? And in the implementation, these things are shared via a so-called transposition table. That's a cache, but never mind that. This is a standard implementation technique for game playing programs. Yeah, but the complication is even equivalent positions need to be evaluated with different bounds AB. And how can we benefit from earlier results? And Fishburne already indicates how you can benefit from it. I'm not going to go into the technical details. I'll just sketch what's going on here. If you have cached a result of an A-B call of a certain position, then you can use that, potentially at least, to shrink the search window of later A prime, B prime calls. So even if you have different A primes and B primes, you may still be able to use the old result that you got out of the previous call with different A's and B's. You may be able to shrink that window when you now come to another call with different bounds. And if you have a smaller window, it means you have a smaller search space. So you're going to explore less of the tree, which of course speeds things up. And so therefore, AB max prime works better than AB max. And that is the standard implementation of alpha beta pruning. And I'm not going to present this. I have come up with a verified version of this version of alpha beta with caching based on the above ideas. Now, that's the end of the linear order explorations. And now I'm going to move on to distributive lattices. And so I assume that people are familiar with lattices. It's just partial orders with a binary supremum and infimum operation. And a distributive lattice, well, the operations distribute over each other. And in case you haven't come across distributive lattices, well, just think sets and you won't be misled. Why do we want to go beyond linear orders? A strong motivation is that you have some games of incomplete information. For example, most card games, you don't see the other player's cards. And that means you cannot evaluate the value of your current position precisely. There are alternatives. Depending on what the other people's cards are, the value of your position is different. And so in order to model those alternatives, of course, think sets and think distributive lattices in general. And so that's the motivation for why this is an interesting extension, generalization to look at. Of course, as a mathematician, the problem is there, and that's why it's interesting, not necessarily because some card games need that consideration. And now let's take a look at the literature, because that's quite interesting to see how different branches of the literature developed quite independently of each other. So the first generalization that I'm familiar with, generalization to distributive lattices, is by Bird and Hughes, two computer scientists. And they start from the specification of alpha beta pruning, or rather the specification of game tree evaluation, and then they derive alpha beta pruning by stepwise transformation. So that's one of the early contributions to this this methodology of refining from a specification to an implementation. Now, it's a bit confusing if you read their papers because they talk about the Boolean algebra. But that led me down some garden path until eventually I realized they don't even use negation. And if you don't use negation in the Boolean algebra, you actually have just a distributive lattice. So that's just for clarifying what they're actually doing. Funny enough, they do not cite Knuth and Moore. So they have their completely own approach, including their own correctness criteria. Now, it takes another 15 years, and then in the game playing community, two people discover or rediscover that alpha beta pruning works for distributive lattices. They're completely unaware of Bird and Hughes' work. And this paper is a little bit sketchy, I find, and yeah, ignorant of the other approach. And then again, 20 years later, a group of people actually built on that paper and really put it on a formal footing. And they are, yeah, this is really quite sketchy, this paper. These people here, they are putting it on a formal footing, and they rediscover the correctness criterion by Bird and Hughes, being unaware of Bird and Hughes. So it's quite interesting to see how different, how long it can take to rediscover things. Yeah. Now, a third interesting, or third, fourth, another interesting formalization of alpha beta pruning you can find in this quite well-known paper in the functional programming community, Why Functional Programming Matters. And this is the same John Hughes, who was also a co-author in this Bird and Hughes paper 2 years prior. And so this paper essentially is a popularization paper that he wrote to show to programmers why functional programming is a fantastic way to write algorithms. And his last example is alpha beta pruning. And so he also derives an algorithm for alpha beta pruning for numbers, not for distributive lattices, from the specification of the game tree evaluator Max-Min. When I looked at this, it struck me that the code looked a bit too simple. And so I wrote to him and said, "Are you sure this is alpha beta pruning?" And John said, "Well, I thought so." And then he said, "Do you have a reference implementation?" And I said, "Yes, here's the reference implementation of alpha beta pruning." And then he quick checked it and he said, "Yes, unfortunately, my algorithm searches more of the game tree than alpha beta pruning does." And I believe the trap he fell into, there are two kinds of prunings. I didn't talk about this, but the real alpha beta that you did see has two kinds of pruning, shallow and deep pruning. What the algorithm by John Hughes in this paper here realizes only the shallow and not the deep pruning. And that simplifies matters. Now, he's not the only one to have fallen into this trap. In the paper by Knuth and Moore, Knuth already tells this anecdote that he was told about alpha beta pruning by somebody in the hallway, and then he reconstructed it from himself, but he reconstructed the shallow variant. And then it took him 5 years to realize that there's also a deep pruning variant. So John shouldn't be too disappointed if somebody like Don Knuth also fell into that trap. Now the question is, how do we generalize both the algorithms and the proofs from the linear order case to the distributive lattice case? And of course, just symbolically, it's very easy. You replace min and max by infimum and supremum. And that takes care of the code. But of course, does it also take care of the correctness proofs? And unfortunately, it doesn't. Because if you look at this criterion, that's one of the two criteria. That's, I think, is the one by Knuth. that doesn't even use min and max. It just uses the ordering relationship. And if you try to use that correctness criterion instead of a linear order, you try to use it in a distributive lattice, it's just not going to it doesn't help you to prove your algorithm correct. The algorithm does not satisfy that specification. And that's not surprising because you can see the specification somehow is relying on a three-way split. Either A, B is less than A, or A is less than B, but less than B, or it's B above B. That works for linear orders, but it doesn't tell you the full story for distributive lattices. And so, so what are possible correctness notions? And what I discovered after the fact is you can connect the correctness notions that we already have to correctness on linear orders, to correctness notions for linear orders, but you need to re-express them. So this correctness notion, that was the one that you saw on the previous slide, can be re-expressed for linear orders as this equality between min-max terms. So if x and y are the same modulo taking the minimum with b and the maximum with a. And you can think of this operator as a kind of a squash operator that squashes the x into the interval between a and b. And once you have re-expressed this relationship here, now you can actually use lattice operations. Similarly, for this bounds specification that I had, which also was in terms of these three-way splits, that can also be re-expressed with the help of minimum and maximum. And that seems to have gone unnoticed in the literature so far. These equivalents seem to be new, and they allow us, and they are equivalences only for linear orders. They are not equivalent for distributive lattices, but we can now try and use this version or that version on the lattices. And indeed, that is exactly what Bird and Hughes did. Although they don't make that connection, their correctness lemma says the result AB of alpha beta pruning and the true value V are the same modulo AB. In which sense? In this sense. That's exactly what we had on the previous slide, but with min and max. And so they cut down this value and this value, put it into the AB interval, and they have to be the same. And of course, again, if you put A to be the bottom value and B the top value, then you just get outright AB equals V. So that is a sort of after the fact reconstruction of where this correctness criterion comes from. Now, you can also, so that was one of the two correctness criteria. That's the one by Knuth. Then there's the other one by Fishburne, the Y bounds X. And that implies the one by Knuth generalized to distributive lattices. So this is really stronger. That's an implication only in one direction. What can we do with it? Well, I tried to do the same thing as the fail soft and fail hard analysis, but now for the lattice case. And I could indeed prove that for lattices, distributive lattices, the alpha beta algorithm bounds the value in the sense of what I showed you earlier. This fail soft version also bounds it, but I couldn't prove that the fail hard version bounds the fail soft version. Here, I'm pretty sure that this holds because I couldn't find any counterexample, and I'll tell you in a moment how I searched for them. So I'm 100% sure this holds, but I couldn't prove it. So this is open work. Just very briefly, I also generalized this, all of the work that you saw before, to negative values. And that's something that frequently, when you read about alpha-beta pruning, it's already specialized to numbers, and it's already specialized to numbers that are that include negative numbers. And so the advantage is, if you look at the original specification just for tree evaluation, you have one function max-min, that's the maximizer evaluating a tree, and we have min-max, and that's the minimizer evaluating the tree. And you can collapse the two into one function if you use negation. Then you just need one function. You don't need two opponents. Of course, de facto, there are two opponents, but you can always simulate one with a negation. You can also do the same thing for the alpha-beta pruning algorithm. So that's one way to get rid of the duality and have just one copy, so to speak. But that's only for numbers. The question is, what happens if you add negation to a linear order, or you add negation to a distributive lattice? And the mistake I first made, I thought the Bird and Hughes, when they talked about Boolean algebras, I thought their negation here, they were using this kind of negation, but that was a red herring. And so you can generalize all of the proofs that you've seen. Well, you haven't seen any proofs, but the proofs of the theorems that you've seen, they can carry over into a setting with a negative values, and you just need to assume that negation is an involution, and it has this De Morgan property for the distributive lattices. So these are not Boolean algebras yet. That stops short of a Boolean algebra, and this is actually something that is known in the literature. This is known as the De Morgan algebra. And so that's a sort of a variant of distributive lattices that moves in the direction of a Boolean algebra, but isn't yet a Boolean algebra. And if you work in that context, then you can generalize this idea of negative numbers to this whole game tree evaluation stuff. And that's the end of the sort of the formal part, the alpha-beta pruning. And I just want to finish with some remarks on this whole verification. And I was working all of the time, both with proving things and with trying to find counterexamples in case I wasn't yet sure. Because there were frequently situations, for example, just simple things like, do I need to assume that A is less than B for this theorem to hold? And then it was very useful to find counterexamples automatically. And so, as I said earlier, I verified all of that in the proof assistant Isabelle, and the two tools that were really essential were two of the most best loved tools maybe. And the first one is called Sledgehammer. And if you haven't heard about it, it's a link to automatic back-end theorem provers provided by other people. It's a mixture of resolution, or rather superposition theorem provers like Vampire and SMT solvers. And in particular, the CVC4 solver prover was a head and shoulders above the other provers in finding proofs in this domain. And I really have to thank both Jasmin Blanchette and Larry, who originally came up with this sledgehammer architecture. I couldn't work without it anymore. And the surprising thing in this context was that if Sledgehammer did not find a proof, then either the conjecture really wasn't provable, or an inductive lemma was missing. So Sledgehammer really was a good guide to saying, I need to do something here. I shouldn't continue proving this stuff, because this particular theorem, either it isn't a theorem, or it just needs an additional lemma, and I first have to think about that lemma. which could be a generalization of what I'm trying to prove. But it was not, I never had a situation where I found that it was provable as is, and Sledgehammer just wasn't capable of doing it, which isn't unusual. That happens in general quite frequently, that Sledgehammer doesn't find a proof, but there is one. But in this situation, it was really quite nice. I could rely on Sledgehammer. If it didn't find a proof, I really had to think again. And similarly for quick check, when I was searching for counterexamples, then invariably quick check was a fantastic guide in the following sense. So this is thanks to Lukas Bulvan, one of my PhD students, and of course the Haskell, and in particular John Hughes, who came up with quick check for Haskell. So quick check generates random, or sometimes not so random, counterexamples and tries and sees if those values are actual counterexamples. And here in my context, I had this nice situation. If quick check didn't find a counterexample, the conjecture was provable. Of course, sometimes I had to crank up the number of iterations quick check was going through. But it really made working in this domain very pleasant to have these almost like oracles that could tell you whether something you were trying to prove was provable or if there was a counterexample. And that's the end of my talk. I'm sorry I rushed through it like this. I would have been very happy to take any questions, but since nobody interrupted me, I just kept on going. But now you have time to ask any questions if you still have any.
Thank you so much. We can start by taking questions from the Cambridge audience, if there are any questions. There is one.
So I have a question that you are studying this under distributive lattices, but then you showed this condition about projecting, that the key was that you could project the value to the interval AB, which is a property of model lattices, which are like weaker. So I wonder if it also holds for model lattices and not only distributive. Do you know anything about it?
No, I don't. I've never explored this, and it certainly would be interesting to see what the bounds of this is and how much whether you can weaken this further. No idea, and I didn't come across anybody in the literature looking at this, but I have to confess that. I have to say that the literature on alpha beta pruning is sort of 95% is, oh, we've implemented this new method and it runs 2% faster, and only 5% at most doing a really nice theoretical study of it. So it's, I wouldn't be surprised if you could improve on this.
So like, do you know how much the proof actually uses the distributivity law?
It's hard for me to say how much. I mean, it does use it, yes, but beyond that, I can't say.
Okay. It's for further exploration.
Yes, yes, and I think I will certainly take a note of that. We can. Yeah, thank you.
All right. Are there any questions from the online audience?
So yes, I have a quick question. So as I understand, you have a lot of proofs in Isabel, and I just wonder, are they somewhere online so you can access them and take a look and
right. I have submitted all of this material to something called the Archive of Formal Proofs, and it should appear in the next couple of days.
Okay, thank you.
All right. Are there any other questions either online or in Cambridge? Oh, there's another question
as well. So I was just wondering if you could elaborate about how the lattice the application you said about the distributive lattice case, because it sounds like in the interpretation of this as a game, the player is allowed to take the least up the path which I guess corresponds to the least upper bound between all of its options, if you like. Whereas if that's like not necessarily a path, yeah, well, how do I interpret that? That might be quite clear.
I must confess, I didn't understand the last part of your question.
Yeah, so hang on.
Yeah.
I guess like in the linear case,
Mm-hmm.
the interpretation is that the maximizer looks at all of its options and then it selects the option which maximizes its score. Whereas in the distributive lattice case, it has a bunch of options and it's trying to none of these options these options aren't necessarily comparable. So it sounds like it's allowed to pretend that there's like least upper bound option it can take. But how do you interpret that?
I don't. I just took my cue from the literature, and I myself a bit at a loss how to interpret that. It sounds to me like you could play both. Could go down both paths and then have the supremum of them. So I'm taking it purely as a formalist. It's there and I'm analyzing it, but I don't have a very good grasp of the game theoretic interpretation of this.
Yeah, fair enough.
So.
And are there any other questions from the online participants? Seems not. In which case, let's thank the speaker again.
Okay. It just in case somebody did think of this, do you have any either for ideas for a symbol or for how to pronounce this relationship where you have these two values x and y, and in one case y is the lower bound, an upper bound of x, and the other case y is a lower bound of x, depending on which side of the intervals they sit. And it's not a symmetric relationship, but it's some kind of approximation relationship, but I don't know what is a good term for it or a good symbol. I don't know if you've any suggestion here.
I've heard of it in a similar case. I've heard of like bounding towards zero or bounding away from zero. Like if you, instead of it being an interval AB, it was just a number zero, then you could say x bounds y away from zero, which basically just means that the absolute value of x is greater than the absolute value of y. So you could just and that sort of gives a hint of which way the sign should be, given it's asymmetric. So yeah, x bounds y away from AB, seems something like that.
You're saying, what is it? X bounds y away from zero or something like that was the...
Yeah, so if you replace the interval AB with just like the number zero,
yeah,
I've heard x bounds y away from zero to mean like exactly, basically that the absolute value of x is greater than the absolute value of y. And I feel like that's the exact same as the situation if you just squish the interval AB to be zero. And that sort of tells you, well, x kind of is greater than y. Like I feel like the sign should point from x to y with that sort of interpretation.
Oh, from x, y being the smaller one because it's closer to zero.
Yeah.
Okay. Yeah, makes sense. Yes, I was wondering whether I need some kind of absolute value, but then I didn't know what to do with starting from an arbitrary linear order. How do you get absolute values or something like that? Yeah, or different. I mean, even the difference. I don't know whether you would. Can you always postulate that there's a metric or something? I don't know.
Yeah, I mean, I don't think you actually need. I'm not saying you actually need to use an absolute value, but I just like as an analogy.
Okay, good enough. Fair enough. Yep. Thank you very much. And I think that's the end then, is it?
Yes, it seems like it.
Okay.
Thank you so much for giving this talk.
Thank you for the opportunity to give it.